In this video, I want to have a look at circular arrangements. So how many ways we can arrange objects or people in a circle as opposed to a line. So the first example I want to look at to introduce this is we have four friends, Alex, Beck, Cass, and Dave, and we're going to seat them around a circular table. We want to know how many different ways that can happen. So if we draw ourselves a diagram to help us visualize this, we've got our table here, and we have four chairs around the table. So let's say that Alex comes along and he's going to choose a seat to sit in. Say this one. So he had four chairs to pick from. Then Beck's going to come along. Beck has three chairs to choose from. So Beck might sit here. So Beck has three chairs. Cass is going to come along. Cass has two chairs to pick from. And then Dave comes along and Dave only has one chair to pick from left. So at first glance, that should be a D there. At first glance, this looks like it's going to be 4 factorial, which would be the same as if we were arranging those four friends in a line. We'd have A, B, C, D, and we'd have 4 factorial ways that can happen. But the difference is, if we'd had that table, so start again, if Alex had come along and instead of choosing to sit on this left-hand chair, he chose to sit in this one as well. Instead, then Beck could come along. Beck could choose to sit here, then Cass, and then Dave. Now this arrangement, these two arrangements, are exactly the same. They've just been rotated. We're just looking at it from a different angle. So Alex could have picked any 4 of those seats, and we could still end up with exactly the same arrangements, just rotated. So what we have to do to get rid of those redundancies, those repetitions of the same arrangements, is we actually need to divide. So this is one way of thinking about it, that to solve this problem, we would have 4 factorial divided by 4. The other way you can think about it is that if we look at our table, where that first person sits doesn't matter. It's completely irrelevant. So they could sit anywhere. And then we're just looking at how many ways we can arrange the other 3 people. Because wherever that person sits, we could just rotate it to match any of the others. So if we just look at that, then we would have 3 factorial different ways that those 4 people can be arranged. And that's exactly what this is, because if we had 4 factorial, that is 4 times 3 times 2 times 1. 2 times 1. Now, if we divide that by 4, our 4's cancel out, and we just end up with that 3 factorial. Our first example says that we've got 4 adults and 4 kids that are to be seated around a circular table. We're asked how many ways can this be done without restriction for part A. So if we have a total of 8 people, we don't mind whether they're adults or kids, we're just looking at the 8 people, then we can arrange them in 7 factorial different ways around that table. So 5,040 different ways. All right, for part B, it says the adults and the kids alternate. Now there's 4 of each. It doesn't matter whether we start with a kid or an adult, but let's just look at one of those groups first. So if we have a look at the 4 adults, they're going to sit in every second seat. So if we just have a look at arranging those 4 adults around that circular table, we could arrange them in 4 minus 1, so 3 factorial, different ways. Then we've got 4 seats left. Those 4 seats are already determined which ones they are. And there's going to be 4 factorial different ways we can arrange the kids into those 4 seats. So the fact that it's a circular table is taken into account with the adults here. We don't need to take it into account with the kids. All right, so if we calculate that, we would end up with 144 different arrangements. All right, and part C, the adults sit together and the kids sit together. So for this one, let's just have a look at the adults as a group, ignoring the circular table. The adults as a group can be arranged in 4 factorial different ways. Then the kids as a group can also be arranged in 4 factorial different ways. Now, we can consider those as 2 separate groups, and we want to arrange those groups around that circular table. So we would have 2 minus 1 factorial different ways that we can do that. So that's just 1 factorial, which is 1. So if we calculate that whole thing, we would end up with 576 different arrangements. Our last example is a probability question. So we've got 4 nurses, 3 engineers, and 2 lawyers seated at random around a circular table. we want to know what the probability is that the 3 groups are each seated together. So all the 4 nurses are together, the 3 engineers are together, and the 2 lawyers are together. So to find probability, I usually like to figure out the denominator first, the total number of unrestricted arrangements. So in total, we have 9 people around this table. So the total number of arrangements would be 9 minus 1, or 8 factorial. Then we consider this case where they're all seated together. So if we have a look at the 4 nurses, there are 4 factorial different ways we could arrange the nurses. There are 3 factorial different ways we could arrange the engineers, and 2 factorial different ways we could arrange the lawyers. Now we have 3 groups that we're trying to arrange in a circle around that table. So we're going to multiply that by 3 minus 1 factorial different ways that those 3 groups can be arranged around that circular table. So if we figure that out, we'll end up with 1 over 70. So there's a 1 in 70 chance that 3 groups are seated together. All right, so that's having a look at circular arrangements.